Okay, number one, quadrilaterals. So here we're working with a parallelogram, and one of the defining features of a parallelogram, even though it's defined as having opposite sides that are parallel, one of the implications is that opposite sides are congruent. And so we know that this bottom one is going to be 13 and the one to the left here is going to be 10 because of that. And here we're being asked to find the perimeter, so we're just going to add those up. So we'll have 10 plus 10 plus 13 plus 13, and that will give us 46C. Now here I'm not sure exactly how you may have learned this one, but I like to think of this as like the side splitter theorem. So if you have a line and you have parallel lines cutting it, it's kind of an application of similar triangles. Because we have these parallel lines, because this line segment here is being cut into equal pieces, the line segment on this side will also be cut into equal pieces. So we'll know that DC, ED, and AE are in fact congruent. And then we're given that the whole length of AC is 54. So then we know it's getting broken into 3 equal chunks there. So 54 divided by 3 is going to be 18. And so we know each one of these pieces, this diagram's a little small, but each one of these pieces here is going to be 18, 18, and 18 because we know they're all equal. ED is one of those pieces, so the length of ED is going to be 18. And then AD goes from up here to here. That's 2 pieces. So AD is going to be 18 plus 18 is 36. Again, the key point here is that parallel lines split these things into proportionate pieces. And since the line on the left is all congruent, or broken into congruent pieces, the line or the line segment on the right will also be split into congruent pieces. Here rest are the diagonals of if the diagonals of a parallelogram are congruent, then the parallelogram is. Maybe the first thing here is we can knock out some things not as even being parallelograms. Kite is not even a parallelogram. It doesn't have parallel opposite sides. And same thing with an isosceles trapezoid. This one might have been tricky because an isosceles trapezoid looks like this. That's a bad drawing, but the diagonals actually are congruent. But it's not a parallelogram, so that's why it's not one of the answers. And then when we think about these other ones here, we can kind of just visualize out a rectangle. I'm not going to go through the proof of this, but the diagonals there are congruent. And a rectangle is a parallelogram because it does have opposite sides that are parallel. And then a square is in the same boat there because it's basically it is a rectangle just with equal sides. And then a rhombus in general will not have, even though they have equal sides, their diagonals will not be the same. You can always see that that the one in the skewed direction there is going to be much longer than the other, so rhombus won't be the answer. So we have rectangle and square. So 4 consecutive angles of a parallelogram must always be, well, let's draw a parallelogram and take a look. So here's our parallelogram, and then I'm just going to draw a dotted line that goes through the top one, and a dotted line that goes through here, and a dotted line that goes through here. Well, this should look familiar from chapter 1. These are parallel lines being cut by a transversal. And when parallel lines are cut by a transversal, the same side interior angles are not congruent, but they will add up to 180 degrees. There's lots of ways to see that, but hopefully that's a theorem that you remember from semester 1, and so the answer is B, supplementary. And you could use the same argument on any one of these pairs of angles. So opposite angles in an isosceles trapezoid are what? Okay, let's go ahead and draw our isosceles trapezoid, and I'm going to do the same thing I did on that last one. I'm just going to draw some dotted lines in here just to kind of remind ourselves what's going on. Okay, so just like the last one, we know that if I mark this one as angle A and this one as angle B, angle A and B are supplementary because alternate, I keep saying that, same side interior angles are supplementary. But then the thing to note in an isosceles trapezoid is that what we really care about in this problem is A, and then we'll call this angle C. So how are those related? Well, we know that angle C is congruent to angle B because it's an isosceles trapezoid. And so therefore A and C are also supplements because B and C are in fact equal because of the isosceles trapezoid. Okay, the first thing we have is to draw a quadrilateral. One thing to make sure is when you draw this quadrilateral, make sure that they go in the order of the numbers listed, like in a clockwise or could counterclockwise, but just at least in order around the figure. And what I mean by that is if I draw 4 points here as a quadrilateral, P is the first point listed, Q is the next one, and then R has to be this one because they have to appear in order. So like P, Q, R, and then S. So the first one is, let's see, PS is parallel to QR, and PS is congruent to QR. I just erased that picture. I'm going to go ahead and draw these each separately here. So we know that PS, so P, Q, R, S. So PR is congruent to QR, and we know that PS is parallel to QR. So we have two segments that are equal on sides and parallel. So from that one we know it's going to be a parallelogram, but these other ones, it won't be, we can't tell whether it's a rhombus because we know nothing about the length of these other sides. We don't know whether it's a rectangle. It could have been drawn, for example, like this and still met the criteria. And so it's just a parallelogram. So now if we have PQRS is a parallelogram like the top one, but we're going to see that PR is perpendicular to QS. Again, PR, that's a diagonal. QS is also a diagonal. So we're going to have a parallelogram where we know that diagonals are at right angles to one another. Well, we know that it's a parallelogram because it says it's a parallelogram, so it's definitely going to be that one. And in diagonals will only, in this situation here, diagonals will only bisect each other if it's in fact a kite or a rhombus. And now kite's not one of the options here, but rhombuses do have diagonals that are perpendicular bisectors of each other. So rhombus would also be a choice here. Here we have PQRS. PQRS is a parallelogram, and in this case we know that the diagonals, saying PR and QS, are congruent. And so we know this is a parallelogram, and the diagonals in general will only be congruent in a rectangle version of a parallelogram. So it will be also true for a rectangle. And then this last one, we'll draw this again, PQRS, and we know that QP is parallel to RS. So QP is parallel to RS, but we're given nothing about the top two sides. Well, all that we know that could be possible here is it could be a trapezoid. For example, I could draw something like this, and these sides would be parallel, but it wouldn't be a rhombus, a rectangle, or a parallelogram because of that. So for that reason, this one is none. Quadrilateral with perpendicular bisectors. I guess you just need to remember that that one's a kite. A lot of times I just find it helpful to sketch these things out. You can see just from the way kind of a kite looks. We're not going to be rigorous here and prove it, but you can see that a kite always has those two cross beams like that, like a cross, and so that's a way to remember that they're perpendicular and have one bisector that gets split here. This one always gets split into evenly down the middle. If it had two diagonals that were perpendicularly bisected instead of just one, this says exactly one, but if it had two, then it would actually be a rhombus or a diamond kind of shape, and then they're both perpendicularly bisected. So this problem is kind of an angle chasing type of problem. I just redrew the diagram to make it a little bit bigger so I could find it, and I'm not going to put the 1, 2, 3, and 4 in here. So now I'm just going to see if I can fill in all the angles that I can find here. Remember, rectangles, this is a rectangle. All the angles are right angles, so this has to add up to 90 degrees in this corner, so we know that this one's going to be 35. And then by alternate interior angles, we know that this angle is congruent to this angle because sides of rectangles are parallel. It's cut by a transversal, so we know that that's going to be 55 degrees. And then for the same thing here, if we think about this being the transversal and kind of turning this on its side, this is going to be 35 degrees. Or you could also back into it that they have to add up to 90. Also in a rectangle, we know that the diagonals are equal and bisect each other. So we know that these are all going to be congruent segments. So since this is this triangle here is an isosceles triangle, we know that they have to have similar base angles. So that's going to be 55. And then we can just fill these in as 35. And there's lots of ways you can get the ones up here, but you can see what's happening. And then to get these central angles of the rectangle, we know that a single triangle adds up to 180. So if I look at this top triangle here, 55 plus 55 is 110. 180 minus 110 will be 70 degrees here. And then these need to form a linear pair supplement. So this would need to be 110 right there. And that should give us all the pieces we need. And then vertical angles are congruent. So I'm going to write these all in, and then we can see what we need. So angle 1 is this one right here, 70 degrees. Angle 2 is this one right here, 110. Angle 3 is this one right here, 35. Angle 4 is this one right here, also 35. Okay, so we have a kite. I've just labeled the diagram for all the pieces that it's given us, and it's told us that KE is congruent to ET, just to let us know which pairs are congruent. And then in a kite, we know that these adjacent distinct pairs are congruent, so IK is also congruent to IT. So to solve for X and Y, I think the easiest thing here is to just see that this IK has to equal IT. So 2x minus 1 equals x plus 4. And we can solve that, move the x over here, x equals 5. Once we know that, so we know x equals 5 here. And then from over here on the right side of the kite, we know that 3x minus y equals x plus 3. Since we know x equals 5, we can go ahead and substitute it in. 3 times 5 minus y equals 5 plus 3, 15. Run out of space here, but 15 minus y equals 8. Bring the 8 over to this side, 7 equals y. So y is going to be 7. To find the perimeter, we just need to substitute x and y back into these sides here. So if x equals 5, 2 times 5 minus 1 is going to be 9. You can just double check. We know this one should be 9, but 5 plus 4 is in fact 9. X plus 3, x is 5, so 5 plus 3 is 8. And 3 times 5 is 15, minus y is 7 is also 8, so we apparently have done this right. So to get the perimeter, we just need to add those up. 9 plus 9 plus 8 plus 8 equals 34. And the question here, is it possible for IE is the long diagonal of the kite, to be 19 units long? And here's where the triangle inequality theorem would come into play. So let's see if is this triangle possible. We have one side of the kite is 9, the other one is 18. Well, the longest, 9 plus 8 is 17. So this side has to definitely be less than 17, and 9 minus 8 is 1, so it has to be greater than 1. So that side has to be between 1 and 17, and 19 is not in that range, so the answer to this one is no. Okay, so here another angle chaser. The measure angle of 2 is 40. Well, what do we know? We're trying to find 1. Well, we know 1 has to be 50, because this is a rectangle. Those add up to 90. We're trying to find 9. We can go get 9 by alternate interior angles here. So we know that has to be 40. And then 10 is going to be 50, because these two have to add up to 90. So the answer for this one would be 50 degrees, 40 degrees, and 50 degrees, respectively. Here, I just drew it again down at the bottom here. Here we know the measure of angle 5 is 130. We're trying to find angle 1, which is right here. We know that these triangles in a rectangle are isosceles, so the two base angles need to add up to 50, because 180 minus 130 is 50. So they're going to be 25 each. And that would give us angle 1. Angle 6 is across here. Vertical angles are congruent, so we know that's going to be 130 right there. That gives us 6. Angle 7, I already got down here from isosceles, which is 25. And then because it's a right angle, it needs to add up to 90. So that one will be 65 degrees.